Today I will present our work, Fly Out the Window, Exploiting Discrete-Time Flatness for Fast, Vision-Based Multirotor Flight. My name is Melissa Greeff, and this work was done with Zhou and Professor Angela Schoellig in the Dynamic Systems Lab at the University of Toronto. The role of the controller in the standard control loop is to determine a commanded action to achieve certain objectives, for example, to fly a path at some desired speed, using state feedback from vision-based navigation. An accurate full state estimate is often challenging to obtain due to typically noisy IMU measurements, an infrequent position update from the vision system due to computational needs, and an imperfect motion model used to obtain high-rate state estimates required by the controller. Despite this, many standard controllers still rely on perfect state estimation from vision-based navigation. To highlight this challenge, we show a typical visual teach and repeat used for multirotor flight. The multirotor flies out and uses visual odometry to create the teach map, and then visual odometry and localization is used to autonomously repeat this path. An IMU and motion model is used to obtain the high-rate state estimates used by the controller. In this plot, we show the discrepancy between the low-rate position estimate from visual localization in green and the high-rate position estimate associated with velocity accelerations and orientation estimates required by the controller. Related work tends to address the challenge of high-performance control under imperfect state estimation by improving the state estimate by incorporating additional sensors, designing robust control to account for the worst-case state estimation error learned offline from data, or performing output feedback control by coupling control and state estimation. Our proposed approach falls within this last category. We present an output feedback control design that uses a window of input and flat output data and bypasses a higher dimensional state estimate. To do this, we exploit discrete-time flatness. In this work, we show that discrete-time flatness applies to the Euler discretization of the multirotor dynamics. Our control design exploits this property and has three key components. We compare the performance of our controller in outdoor vision-based flight experiments with controllers that rely on a full state estimate from vision-based navigation. Our hardware setup includes a DJI M600 Pro, a Ronin gimbal camera. All computation is done on board on the NVIDIA TX2, and we use a Stereo Labs camera. The black L path is the teach path to be repeated at a desired speed of 3 meters per second. We show the autonomous closed-loop performance using vision-based navigation and PD control in green, flatness-based model predictive control in blue, and our proposed discrete-time flatness control that uses output feedback in red. We show the autonomous closed-loop performance using vision-based navigation at a desired speed of 9 meters per second. The PD controller in the top video goes unstable. We compare the path error over multiple trials at desired speeds of 3, 5, 7, and 9 meters per second. We see that our proposed controller, discrete flatness in red, outperforms related controllers that rely on noisy and inaccurate state estimation. Our proposed discrete-time flatness controller can reach speeds up to 10 meters per second. We extend our controller for three-dimensional flight. To summarize, we demonstrate that the Euler discretization of the multirotor dynamics is discrete-time flat. We use this to design an output feedback controller that uses a window of input and flat output data. In outdoor multirotor flight experiments, we show the application of our discrete-time flatness controller to vision-based flight at speeds up to 10 meters per second and how it outperforms similar controllers that hinge on accurate full state estimation, achieving up to 80% path error reduction.